Okay, now, do you hear me, guys? Oh, okay, cool. So sorry about that. Some issue. So hello, everyone. Nice to see you. Hope you're doing well. So last time we introduced entropy as a new state parameter and defined that entropy is some kind of measure of disorder of the system, and its change defines like the statement that in isolated system entropy should increase or remain constant for irreversible and reversible processes respectively, defines the direction of thermodynamic processes, and that is actually another form of introducing the second law of thermodynamics. So we defined the equation which defines the change of entropy and also like differential of entropy as a state parameter, and derived equations for change of entropy for ideal gas when we consider different thermodynamic processes, isobaric, isochoric, isothermal, adiabatic. It is important to mention, since we will recall it also in today's discussion, that we started from isobaric process, because in isobaric process we have change in temperature and change in volume, means we have both heat exchange and work done by the system. So taking this into account, the differential of entropy was defined as a sum of two terms. One, like first one, responsible for change in temperature, second one, change in volume. So all other processes can be analyzed based on this definition, this equation, by the way of simplification, because we can, for instance, for isothermal process, we don't have a change of temperature, so this first term is equal to 0, so we deal with the second term. We need to integrate it, and for isochoric process, when volume remains constant, the second term is equal to 0. So we deal with the first one. So today, so all this discussion during last time was based on the relationship between entropy and macroscopic parameters. So today we are going to continue our discussion of entropy, but in terms of its relationship with microscopic parameters. To be more specific, with a number of microscopic states which describe the macroscopic state, and that term is called thermodynamic probability or statistical weight. So let us give an introduction to this and find relationship between this entropy and statistical weight of a macro state, which is defined by number of micro state parameters. Okay, let me change the camera to our slides. And our discussion of entropy today's from the microscopic point of view, we will start from introducing some model system for our discussion, and it will be some cylinder with thermally isolated, we can just delete this one, with thermally isolated walls. There's no heat transfer, but it has some membrane inside which divides this cylinder in two volumes. We have some initial volume, and also like total volume will be V final. So in this initial volume, below the membrane, we have some ideal gas which occupies all this initial volume. So now let us count the number of microstates by considering the variety of molecular locations available to the molecules of this ideal gas in initial volume VI. So let us assume that each molecule occupies some microscopic volume Vm. That's volume of a molecule itself. The total number of possible locations of a single molecule in a macroscopic initial volume Vi will be given by Wi, so we have small w, and that is equal to Vi divided by Vm. So we actually define how many of these molecules can fit in initial volume Vi. That defines how many microstate parameters a single molecule can occupy inside this volume, initial volume Vi. Assuming that the probability of occupying each point in space is equal. Now, so this is about a single molecule. Now let us consider what will happen if we have two molecules. So there is Wi ways to locate the first molecule and Wi ways to locate the second molecule. So actually we will have Wi multiply Wi, that is equal to Wi squared, microscopic parameters, like microstates for these two molecules. We assume here that probability of molecules to occupy the same point in space is negligibly small, so we don't consider that option. So actually we have total number of microstates for two molecules, Wi in the power of 2, which is 2 in our case is number of molecules. Assume that we have some arbitrary number of molecules, and in that case we can introduce this statistical weight, capital W initial, means the total number of macrostates which can describe macrostate, given macrostate, initial macrostate, assuming that we have n molecules. That will be equal to Wi small in the power of n. Again, we assume that molecules do not occupy the same points in space simultaneously. So that can be given as Vi divided by Vm in the power of n. So let us assume now that we eliminate this membrane. So these molecules of the gas will uniformly fill whole container, and we will deal already with volume V final. So in that case, the thermodynamic weight or probability or the statistical weight for final macrostate with volume Vf will be given as W final in the power of n, and that will be V final divided by Vm in the power of n. Since number of molecules n remains constant, Vm also doesn't change, and V final is larger than V initial. We can also say that W final is larger than W initial. There are more possible microstates which describe final macrostate in comparison to initial microstate in this example. So now let us consider what will be the ratio of statistical weight for final and initial state, W final over W initial, that is equal to V final divided by Vm in the power of n divided by V initial over Vm in the power of n. Therefore, we have V final over V initial in the power of n. So let us now keep this in mind. So let's rewrite it on the next slide, and we will proceed further. So W final over W initial is equal to V final over V initial in the power of n. So now let us do the following. Let us take natural logarithm of left and right side and multiply by Boltzmann constant also, left and right side. We will have k times natural logarithm. Sorry. Wf divided by Wi, and this is equal to k multiply natural logarithm V final over V initial in the power of n. So that should be like this. Now, taking into account the properties of logarithm, we can write here k times n times natural logarithm V final over V initial. Also, we remember that total number of molecules, which is n, can be given by product number of moles times Avogadro's number. So that is equal k times new number of moles times Avogadro's number, Na. And here is natural logarithm of V final over V initial. Do you remember what will be the product of Boltzmann constant and Avogadro's number? We discussed that during this topic of this equation of the state of ideal gas. So that is universal gas constant. If we have a product of Avogadro's number and Boltzmann constant. So that will be equal to nu times R times natural logarithm V final over V initial. So now we have expression of like some relationship between micro state parameters and macro state parameters. So here statistical weight and volume, initial and final respectively. We can also write it as follows. It will be K times natural logarithm of W final minus K natural logarithm of W initial is equal to nu times R natural logarithm of V final over V initial. So let us keep this in mind, this equation. And we will come back to it a bit later. Let us now recall what will be the change of entropy for such process when we take out the membrane and our gas starts to spread, expand in the free space, because before we took out the membrane, the space above membrane was empty. There was nothing there, vacuum. So in this case, change in internal energy is, we know it's heat plus work. Actually, we, as you remember initially, we specified that the walls are thermally insulated. There is no heat exchange. So Q is equal to 0. And with work, so we have expansion. Volume changes. We always claim that, okay, if volume changes, there is some work done by the system. However, not in this case, because work is equal to P times delta V. And we have change of volume, but the thing is that this expansion of gas was happening in free space. There is no pressure which will prevent this expansion. Since P is equal to 0, there is nothing in the area above membrane. Then this expansion happens in free space and nothing, work is not done. So it's also equal to 0. Means that change in internal energy is equal to 0, and that means that temperature remains constant. If you recall from our previous discussion, when we derived equations for the change of entropy for isothermal process, So we had something like this. There was change of entropy. So this is for isobaric process in general case. Was equal, we can also write that it's integral from initial to final state, dq over t. And we have shown for isobaric process that it's equal to cv times nu, natural logarithm t final over t initial plus nu times r, natural logarithm of v final over v initial. So we had this last time, and if temperature is constant, the first term is equal to 0, it doesn't contribute. So we define change of entropy by the second term. So we can write here that delta S is equal to S final minus S initial is equal to mu times R natural logarithm V final over V initial. So we see this equation for the change of entropy. And now if we come back to previous slide, we see the same equation which relates macro and micro states of this ideal gas. So we can write that this is equal to change of entropy, and actually taking this into account, we can write here that k times natural logarithm of w final minus k natural logarithm of w initial is equal to s final minus s initial, that's equal to delta s. So if this is true, and we have shown that it is, we can write that S entropy is defined as K times natural logarithm of W, natural logarithm of statistical weight, or in other words, number of microstates which can describe given macro state. So that is relationship between the microscopic parameters and entropy. And since the number of microstates which can describe macro state increases when we go to some thermal equilibrium condition, and we know that entropy when we go to some thermal equilibrium condition in isolated system always larger than 0 for irreversible processes or equal to 0 for reversible processes. We see that we can also formulate the second law of thermodynamics in that way that thermodynamic processes have such direction in isolated system, which leads to higher statistical weight or higher microstates, which describe macrostate thermal equilibrium condition eventually to which this system will come. And that is because we have kind of proportionality between statistical weight and entropy. And we know that entropy always increases in isolated system if we consider some irreversible processes in this isolated system. So taking this into account, this relationship between change of entropy and initial and final statistical weight, we can go further and consider the ratio between statistical weight of final and initial state for ideal gas during different thermodynamic processes. So we can write that change in entropy is S final minus S initial is equal to K times natural logarithm W final over W initial. So the ratio W final over W initial is equal to exponent delta S over K, and that is equal, we know that delta S is defined as integral from initial final dq over t. So we can write here exponent 1 over k integral from initial to final state dq over t. So that is in general form, but we know from previous discussion, we considered this integral, and also we recalled it here. This integral, where is it? Yeah, this integral is equal to the sum of two terms responsible for change of entropy because of change of temperature and change of volume. So that's why for isobaric process, P is equal to constant, we have the following: WF over WI is equal to exponent CV times nu divided by K, natural logarithm of T final divided by T initial, plus nu times R divided by K, natural logarithm of V final over V initial. So that is true for isobaric process in ideal gas. Also, let us consider isothermal process, T equals constant. Sorry about this. Somehow everyone wants to talk during the lecture. So at constant temperature, the ratio for statistical weights for final and initial macrostates will be given, will be determined only by second term, because in first term we have, like, it will be 0 because temperature doesn't change. So we can write that it's equal to exponent nu times R divided by K natural logarithm V final over V initial. And now we need to recall that R divided by K is equal to NA, and nu times NA is actually total number of molecules. And that's why we get exponent N times natural logarithm of V final over V initial. Taking into account properties of logarithm, this N can go to the power of argument of the logarithm. And if we take exponent of natural logarithm, we will get argument of this natural logarithm. So that will be equal to V final over V initial in the power of N. Or in other form, as we did previously, we can also write that it will be unity plus delta V over V initial divided by, and everything in the power of n. So that is the definition of this ratio of statistical weight for initial, final, and initial macrostates of ideal gas for isothermal process. Let us also consider one more process, which is isobaric. V is equal to constant. So in this case, we can see here that only first term will contribute because second will be equal to 0, assuming that volume doesn't change. So we can write that W final over W initial is equal to exponent CV times mu divided by K, natural logarithm of T final over T initial. So we follow the same procedure. If we take exponent of natural logarithm, that will give us T final over T initial in the power CV times nu divided by K, or it will be equal to unity minus delta T divided by T initial in the power CV times nu divided by K. Okay, so summarizing our today's discussion, we considered this model system with a membrane in between which divides volume to initial and final, which is final equals to total volume of the container. We have shown that the statistical weight of final macrostate, in other words, number of microstates which describe final macrostate is larger than statistical weight or number of microstates for initial macrostate, which is described by smaller volume B initial in comparison to B final for final state. So also we have shown that there is a relationship between change of statistical weight, like microstate parameters, with macrostate parameters, volume, initial and final. From other side, it was possible also to show that for this given process, when we take out the membrane and a gas expands to the free space, change of entropy is defined by the same equation as change of natural logarithm of statistical weight. So we can equate change of logarithm of statistical weight times Boltzmann constant to the change of entropy, and define entropy as Boltzmann constant times natural logarithm of statistical weight of given macrostate parameter. Assuming that definition of the second law of thermodynamics, when which can be formulated that entropy always increases or remains constant in isolated system for irreversible or reversible processes, we can also formulate second law of thermodynamics in that way that thermodynamic processes, they run in that direction, which will lead to macro states with higher statistical weight or higher thermodynamic probability. Also taking into account the previous derivations of change of entropy, we could derive equations for the ratio of statistical weight of final and initial macro states for different thermodynamic processes in ideal gas. So in particular, for pressure, temperature, and volume. So with this, I would like to finish our today's discussion. If you have any questions, you're welcome. So I would like to remind you that, thanks, that we will have our final exam on Monday. We will still send you an email. I have already received a bunch of questions, which topics will be covered by this final exam. There will be all topics covered. So it will be some focus on chapters on molecular physics and thermodynamics, since it was not covered by previous, these chapters were not covered by previous midterms. However, problems in this list of 6 problems which you will get for final exam, there will be problems from all chapters with equal probability, all other chapters besides molecular physics and thermodynamics, where will be some focus because we want to check this additionally, since we didn't check it in midterms.
Okay, thank you.
Okay, guys, then thank you very much for your attention. Have a good evening, and yeah, see you on Friday. Bye-bye.